markers is good at all. Yeah, use a Sharpie. This is permanent notes, children. We want to talk about today fossils and the geologic time scale. We talked without it being on video on Friday about the methods that fossils can form. So we're going to kind of review that quickly here, and then we're going to move on to the importance of fossils and how we compile them all together using the fossil record into the geologic timescale. And we're all going to take notes over this. Every single last one of us is going to take notes over this. At least about the things that they don't know. And one of the lovely things about how I know they don't know is they just told me. Okay, the geologic timescale and how it relates to fossils. What a fossil is? Well, let's look it up. What's a fossil? Is it always bones? I mean, we think there's this romantic kind of poetic notion of fossils as the T-Rex, but that's very rare. I'm almost certain there are fewer than 100, and I'm 100% certain there are fewer than 1,000 Tyrannosaurus Rex fossils in the world. There just aren't that many. So that's not a very common fossil. Let's give a little bit broader, but also a little bit more detailed description of what a fossil is. Miranda, let's start with you.
An organism remains. Because plants don't have bones, but they have fossils.
Yeah, yes, you're right. I would say that's much better than calling it bones, certainly. The only problem I have with yours is that does it have to be their actual remains?
No.
We talked about this. No. So let's not call it an organism's remains. Let's call it
Evidence.
Lucas, that's great. Evidence of the... I'm not even going to put remains because there's another... Remember we talked about trace fossils, which would be evidence of behavior. Evidence of ancient... I'm going to give you the definition of ancient that's used by paleontologists. Fossils we usually say must be at least 10,000 years. So we're going to say greater than 10,000 years. Organisms. Evidence of ancient organisms. What kind of evidence would there be? Well, let's talk about, there's two broad categories, first of all. There are body fossils, and there are trace fossils. This is one way that we can classify fossils. And what I mean by one way, the thing about, instead of fossils, pretend we're talking about 8th graders. We could classify 8th graders based on their height. For instance, we could organize you all by your height, couldn't we? You might have the similar heights, but you could still organize each other. You could organize the class by height. I could say 8th graders are greater than 5 feet tall and less than 5 feet tall. That would be one way to categorize them, wouldn't it be? Right? You with me so far? Another way to categorize them is their method of preservation. That's another whole way to classify them. This would be like saying hair color. So it's not like the type of preservation is specific for body fossils or trace fossils. This is a whole different way to categorize them than this. Just like a whole different way to categorize 8th graders is height or hair color. I've done those in different colors so that you realize that they're different because you have a little animal brain. Okay, so what is a body fossil? Let's go back to this one. What's a body fossil? Bones. Does it have to be bones?
Hair. Yeah.
Hair. Soft and hard parts. Shells. Yeah. Any part of it. Anything that tells us evidence of... No. Evidence... I'm going to say this word. Evidence of morphology. What? That's a science word that we use all the dang time. And this just means morphos is the Greek word for shape. Ology is the study of shape. Evidence of how they look, how they would have appeared, how their body structures actually were, how their body structures were. Evidence of morphology, how their body structures appeared. If you need to define morphology on the side, that's fine. It's basically appearance. I could have put evidence of appearance, but this is more scientific and I like it better. Morphology. Morphology. Oh, appearance. You could say appearance. It's the way they looked, the way they actually would. Yeah, like morph, sure. The way they actually would have appeared, and not just the way they appeared on the outside, but the way their organs were structured. Sometimes, if we're very lucky, the way their organs were structured. If we're very, very lucky, the way their nerve system and blood vessels were structured. That rarely happens with fossils, but it does happen. So the evidence of morphology, the evidence of their structure, the evidence of the way they were structured. Trace fossils are evidence of. You can probably fill in this blank. all the
Shape of body.
behaviors. That's much better. Behavior, because it can be their feet. Although when you phrase it that way, that makes it sound a little bit on the creepy side, Garrett. I wouldn't go around saying that. But the evidence, it wouldn't just be their feet. We're not really, because that would really be a body fossil, wouldn't it? The shape of their feet is a morphology. But the evidence of their behavior, what are we learning about when we see, you're thinking about the footprints, which are a classic example of trace fossils. They're how fast they could go, their stride length. But listen, Tommy, how many toes they had is morphology. That's body fossil. But we could learn about their stride, their gait. Yeah, how they stand. In fact, if you look at old, here old meaning before the 90s, but that's older than me, so I'm going to say old. If you look at old dinosaur books, like I used to when I was a kid, you'll see a T-Rex shaped kind of like, and you probably will still see a T-Rex. Oh, golly, this is not a good drawing of a T-Rex. Come on, give me a break, kids. I'm doing my best. You'll see a T-Rex shaped kind of like this. That is cute. There we go. That's cute. Yeah. You'll see. Oh, I'm glad you brought that up because Godzilla was based on this idea of a T-Rex. People thought they stood upright and their tail was used as balance, kind of like, I can't even really think of it, kind of like a kangaroo. Usually standing upright with their little paws, and their tail was used as balance. Their tail was used as balance, but now we realize through analyzing gait, analyzing footsteps, the way that they actually moved, and we know now that they probably were more like, well, I say
It looks like he's just walking now, with no arms.
So I'm trying to draw the same size of Tyrannosaurus Rex here. A little smile. But they moved more like this, with their tail used as balance while they were running. So, and we know this, or as much as we know anything, we know this because of the way that their footsteps were when we found trace fossils. So we used to think they walked around like people, basically, with a tail on the back. But now we know they were more like, and obviously its little legs were not used for the actual running part, but they moved more like how, well, for instance, if you've seen Jurassic Park, this is how they move in Jurassic Park. Well, that's based on fact. Unlike Jurassic Park, we have found body fossils. I have seen with my own eyes, which is not right here, with my own eyes, I have seen with my own eyes that this was actually feathered. Yeah, feathers. Most dinosaurs by the Cretaceous, which is when Tyrannosaurus Rex lived, had feathers. And what I mean by I've seen with my own eyes is that I was at a fossil dig in Casper, Wyoming, where they had recently discovered, this was 2014, so it's less recent now than it was then, but they had recently discovered a new Tyrannosaurus Rex fossil by Lance, Wyoming. And while they were excavating this, and I was there for this, I saw there was like, I don't know, so it looked like a blob of rock, and there was some ribs here, and there was the outline of its abdomen here, and I saw with my own eyes little imprints, and it was prettier than this, but imprints of feathers. I know, as much as I know, like, okay, let me give you another example. If I found at a football game where it had been rainy, I found someone's shoe that was shaped like a shoe print. This is a shoe print. You know what I'm doing here. Yeah, this is supposed to be a good shoe print. I would know, like, okay, let's say,
Size 14.
yeah, if it says 8 here, I could look at this shoe print and say, oh, someone has a size 18 shoe. I wouldn't say that because I would be wrong. Someone has a size 8 shoe, I would say. Do I really know that? I mean, like when we get down to what knowing means, do I really know that someone has a size 8 shoe? Well, as much as I know anything, I do. In the same way, I know, because I've seen with my own eyes, that this Tyrannosaurus Rex had feathers. If you think this is better evidence, that's fine. But recently, since I've started teaching this class, there has been discovered, we talked about amber on Friday, there has been discovered an amber, a big old blob of amber, with not Tyrannosaurus Rex, but another Cretaceous dinosaur trapped in it that literally still has feathers. There are feathers on it.
That doesn't look as cool. I know, right? It's like scales.
I think it's way cooler. I think it's way cooler. I think it's way cooler. And what is that? And what is that? It gets into something. Shh. That gets to something even more important. What does that then tell us? Very, very accurately. Yeah. That listen. And I will fight people about this, but I think this is so beautiful and poetic. That Asher, my 2-year-old son, his dino nuggies are literally made of dinosaurs. They're not just shaped like dinosaurs. They are made of dinosaurs. A chicken is a dinosaur. A chicken came from dinosaurs. In every way that we can say, in the same way that you came from your grandma, a chicken came from a dinosaur, just a little bit further back.
Tell me when I eat those dino nuggies, I'm being actually.
That is, yeah. The only reason, actually, let me tell you, this is not what this class is about. But the only reason we call that group of birds aves, which is Latin word for bird, instead of dinosauria. No, this is not a joke. This is the actual name of the clade of dinosaurs, is Dinosauria. The actual name for the order of birds is Aves. The only reason we did not, when we discovered that was true, when we discovered that that birds were all descended from dinosaurs, the only reason we did not rename it as they're all dinosaurs, now like officially called dinosaurs, is because this word, and this is how the biological naming works, was coined first by Carolus Linnaeus in the 1700s. He called them all birds. When people first started classifying things, he classified them as birds. And then maybe 10 years later when these were classified, they were called dinosaurs. And if those had been reversed, if he had named dinosaurs first, in biology you give precedence whoever named it first. If you find out something later was actually a part of this other group, you give precedence to whichever one was named first. And so the only reason we don't currently call them all dinosaurs is because this was named first. I don't know, you can look it up, 1760 maybe, I don't know. And this one was 1803. I don't know. I'm making both of those up. But this one was named later, and so we don't call them this, even though we know, boop, all of them either died or became that. Which really, if you think about it, makes more sense. Like, what is the statistical likelihood that any event on Earth would wipe out all of the dinosaurs? It's pretty low. But it wiped out all of the dinosaurs that didn't then immediately here being a million years or 10 million years, adapt and become smaller birds, which is beautiful, I think.
Their front arms turned into wings.
Yeah. I have read this. I will. You can look this up and verify it. I don't have a source to cite, but I did read this from a scientific article. The closest living relative of the velociraptor is the chicken. It just is. And if you look up, here's another piece of evidence for this. And we're going to get all in. We're really kind of getting astray from what I really want to talk about. We get into all of this during the next couple lessons. But if you look up a picture of a rooster that has no feathers, like a living rooster that has been plucked of its feathers, it looks like what you think of as a velociraptor. It looks like a Jurassic Park velociraptor. Also, here's another piece of evidence. Sometimes, not super frequently, but not extremely rarely, sometimes a fluke of a chicken is born with teeth.
What? Actually?
Yeah, and it looks like a little dinosaur. JJ, you had a question for a while. What is it?
Okay, if we live with dinosaurs, would you have one as a pet?
We do have them as pets. Chicken.
Would you listen to anything I said?
Question. It's a trick question because most people would say no, and then they say you already have one.
You already have one. It's a peacock. I would have a peacock if they were allowed in town.
What about like Komodo dragons? Because they literally stand up on two legs to fight people.
Yeah, but no, JJ, you're making kind of, I would say, I think you know this is a silly question, but people think of dinosaurs as like big reptiles, but they're actually more like much more closely related to big birds. They really are. So we think of when you're young and wrong about everything, you think of an alligator as like a modern day dinosaur, but that ain't it. It's really the chicken is the modern day dinosaur. Hemingford people. That's exactly right. Thank you for bringing that up, Lucas. Anyway, that's one way. This is one way that we classify fossils, between body fossils and trace fossils. The other way that we classify them is method of preservation. You're going to have to probably look these up on your own, but we have these things. Mineralization. I'm using the same terminology as your book. We sometimes also call this petrification. Carbonization. It says amber fossil. I'm unwilling to put that in there. I'm going to put original soft parts and original hard parts. Carbonization. Casts and molds. Those are the ones that I'm familiar with that I would like you to know. to verbally describe these briefly. You're going to have to look them up on your own to get them in your notes probably, but or you could write down what I'm saying, that's fine. You do need to know how each of these occurs. You're either going to have to look it up, or you're going to have to write down what I say. In permineralization, and another thing is, let me be more clear for people who are viewing this, who aren't in this class, that maybe they think I'm shortchanging you in your education. We did talk about all of these Friday. I mean, we at least talked about these 5, not so much carbonization. But permineralization is where, as you know, all critters have holes. And I don't just mean mouth hole, etc., without getting too gross. They have everything is pore space. Inside your body, there are holes among and betwixt everything. There's nothing. You're not a solid object. You are a collection of holes with some guts around them. But these holes, when a thing dies, very, very rarely. Remember, fossils are exceedingly rare. We talked about on Friday the dead deer that I saw on my trail several years ago, 4 years ago, completely gone now. It's very rare for a thing to be fossilized at all. But when it's fossilized, one thing that can happen is its dead body gets into some mud or some wet sand or something, but there's something there with minerals and water both. And as it decays, the minerals and the water go into the pore spaces of the organism. And then as the organism continues to decay, those pore spaces are full of minerals. And they harden and they become rock. And then even when the organism itself is completely gone, the rock is still in the shape of that critter. Aye, aye? Does that make sense?
Aye.
That's called permineralization. How long does the critter last? No. Answer me again. How long does the critter itself last? The physical object, the critter that died, how long does that last? Yeah, maybe 4 years, maybe 20 years, maybe 1,000 years at the very, very most, I would say. But because now its pore space has been filled with rock, how long does the rock last? Well, it can last, once again, that could last less than 1,000 years, but usually it lasts much longer. Rocks are much more resilient objects than the critter itself is. And so the rock that's in the shape of the organism, so it's not it's not the organism at all. If this dinosaur that was being dug up, that I watched them dig up, these are not ribs. These are rocks that happen to be in the shape of ribs. You see what I mean? They're not the actual ribs of the Tyrannosaurus Rex, but they are evidence of the ribs because they're the exact same shape that those ribs were. Carbonization is what happens when, usually in a wet environment, a thing dies. As with all of these, a thing dies. We don't even really have to say that. But a thing dies, and its juices kind of exude out into the sedimentary rock. I have a great example of this in the lab that if I had remembered, I would have brought in. This happens a lot with very flat organisms. Fish, leaves, these kinds of things are carbonized a lot. What happens is there's some sediment here. There's a dead fish on top. Some sediment gets on top of that. As the fish dies, well, it is dead. As the fish decomposes, its black little death juices get out onto this sediment because they're pressed out by the sediment above, and this becomes a little dead fish juice sandwich. Which is another thing you can ask for at Subway if you want the tuna sandwich. You can say, "Give me that dead fish juice sandwich." And like, "Aye, Captain." Anyway, this rock then has kind of almost like an ink print of this organism on it. It's carbonized. It's the carbon from this organism is what's left behind, and it's left on this rock. And I have examples that I would like to show you, but I didn't bring them. We talked about these two on Friday. These are somehow, this one borderline miraculously, this one a little bit less so, but only for really quite young quite young fossils. The minimum age for a fossil is 10,000 years, so maybe something like between 10,000 and 100,000 years, we might find fossils that are original hard parts. It'd be extremely rare to find something like that with original soft parts, except in the case of amber, perhaps. And then these two, they're pretty easy to understand conceptually. I think a mold is what happens when you have some soft sediment, clay, for instance. So imagine you have a little ball of like modeling clay, some wet clay, okay? Are you imagining? And then you have, and if I remember to bring any of these materials, it would have been better to see, a little critter dies, and then it gets pressed into the clay. You can imagine the clay getting something pressed into it. Now, as that critter decomposes, what's left? There's a hole with the shape of that organism, right? There's in the clay, there's a hole the shape of that organism. Once again, it's in rock, so this is going to last a lot longer than the organism itself. That's called a mold. The mold is a negative impression. And I don't mean a negative impression like if you meet a creepy guy at the grocery store, he gives you a negative impression. I mean that it's a hollowed out, it's a hole in the shape of the organism. It's negative. It's a hole in the shape of the organism. Sometimes that hole in the shape of the organism, which is a mold, gets filled with sediment of its own. And then when that sediment comes out, that's called a cast. That's a positive
So that's like the
replica almost.
or the fossils.
Yeah, like if you go to an actual museum, very rarely do they have even permineralized fossils. Even though this is actually rock, very rarely do they actually display the actual fossil itself. Usually what they do is they make a human version of this. They take some plaster, they squish the fossil into it, they let the plaster dry, they fill that up with foam rubber or resin or plastic, and then when that dries or hardens, they take that out, and now it's a positive, the same shape. I don't know. Does anyone have, I'll just use my resistance band. This is going to be the worst demonstration ever. This is some soft sediment, okay? Some nice soft sediment. This is a fossil, or this is a dead thing. Okay, this is a dead thing. It squishes into the soft sediment, and then it decomposes. Now there's the shape of a dead thing in the soft sediment. This is called a what? Mold. And then more sediment piles on and fills in that hole. Or resin, or whatever, the plastic. That wouldn't happen in the wild, but that's what they use in museums. Plastic fills in this hole, and then when you take it out, it's the same shape as the original thing. It's a cast. It's just not the original thing. This is also how statues are made. That's not how my unicorn statue was made, but it is how some statues are made. Have you seen like that ram statue in front of the building? That was made in a method called the lost wax method. So what happens is someone starts out with a block of wax, a big block of wax in that case, and they use a knife and they carve the shape that they want. Nice. It's a ram. It's a ram. We're supposed to call him a name. I can't remember. But they carve that ram exactly like it will appear, but it's made of wax. And then they smoosh some concrete or sand or whatever around it. They make a big old block. They put their ram shape in, and then they pour molten bronze on everything. And the molten bronze melts the wax, but it doesn't melt the sand. And so now, when the wax runs out, it's left with just bronze in the shape of that wax. And then when the sand comes off, when they take off the mold, what's left is just a bronze copy of the wax thing from before. And that's how statues are made. It's this exact same process. It's just used for fossils in nature. What up?
I see this guy on example he took anything else like metal and he pours it into a big bucket of Orbeez.
Okay.
And it's got like a bunch of, it's a big metal thing. And it's got a bunch of holes in it.
That's cool.
Like a bunch of,
That's this. That is exactly cast and mold. It's just that doesn't happen with metal in real life, not usually at least. Okay, Sage, I know we ran out of time. This stuff you already knew about or was kind of easy to understand. The actual things that were difficult, we didn't get time to get to. Let's continue this tomorrow.